Please, Christoph.
Okay, so
Yeah.
okay, so your name and your definition of helper differs from mine. Okay.
So I'm supposed now to announce the first video, right?
Yes.
Okay, so I was just looking up here. Okay, sorry for all this. So the first presentation is a paper about SMT-based model checking of max plus linear systems, and the paper is by Muhammad, Andrea, Alessandro, and Alessandro. I used now the first names. I'm very sorry for that. Yeah, so please start the presentation.
Hi everyone, my name is Muhammad Sifal Mufid. I'm a PhD student at Department of Computer Science, University of Oxford. In this ConcurB conference, I will present my recent work titled SMT-based model checking of max plus linear system. This work covers the novel procedures to solve formal verification over max plus linear system, the class of discrete event system defined over max plus algebra. The other authors of this work are my supervisor Alessandro Abate and also Andrea Micheli and Alessandro Cimati of Fondazione Bruno Kessler, Italy. For the first part of this presentation, I will describe some notions and properties of max plus linear systems. However, it is necessary to mention max plus algebra. So, max plus algebra is a summering over a set Rmax, which is a set of real numbers joined with minus infinity. There are two binary operations for max plus algebra, O plus and O times. A O plus B means the maximum between A and B, while A O times B equals A plus B. This operation can be extended to matrices in the natural way. For a square matrix A, this notation refers to the k power of A. From the max plus algebra, one can define a discrete event dynamic system with these formulations. Here, A is the state matrix, X is the timestamp vector of the discrete event, while K is the counter event. The application of max plus linear or MPL system can be found on the model where the time variables are essential, such as transportations, manufacturing, and scheduling. The other application deals with biological systems. Let's have an example. Here we have a railway network with 2 stations and 4 routes. There are 2 rules for this network. First, the departure of a train from a station must wait for the arriving of all trains to the station in order to allow the traveling of passengers. Second, the trains must depart as soon as they are allowed. By denoting xik as the time instant of k plus 1 departure from station Si, we have the following inequalities. Then, by the second rule, we get the equation which later can be expressed as metric operation as follows. If, for example, the initial departure from station S1 and S2 are happen at 0 and 1 time unit respectively, then we get the following sequence of vectors. The following are some basic notions in MPL system. The precedent graph of an n-dimensional max plus matrix A is a weighted directed graph with nodes integer from 1 until n, and there's an edge from j to I with the weight aij if the corresponding element is not equal to minus infinity. If the precedent graph of matrix A is strongly connected, then A is irreducible, otherwise it is reducible. The eigenvalue of irreducible matrix is always unique and equal to the maximum average weight of circuits, a path in the precedent graph that start and end at the same node. For an irreducible matrix A and its eigenvalue lambda, when we take the power of A, there exists L and C such that this condition holds. The smallest value for such L and C are called transient and cyclicity, respectively. Next, given an MPL system and an initial vector x0, the sequence of vectors x0, x1, and so on is called an orbit of x0 with respect to matrix A. Furthermore, if there are real number alpha and non-negative integer kl such that this condition holds, then such sequence is called a KL lasso, and L is called the loopback bound. From this illustration, we can say that in KL lasso, the vector at bound k plus 1 is equal to vector at loopback bound L after adding the values with alpha. In general, we can say that transient is the starting point of periodic behavior in the MPL system, while cyclicity is the period. For instance, from the previous metric, the corresponding transient and cyclicity are both equal to 2. It is possible that the dynamics of an MPL system starting from an initial vector has smaller transient or cyclicity. For instance, from this initial vector, its corresponding orbit is periodic with transient 1 and cyclicity 2. We call the transient and cyclicity computed from the metric as the global ones, while the ones computed from an initial vector are local. We can define the global transient as the supremum among all local transient and the global cyclicity as the least common multiple of all cyclicity. We can define the similar notation for the transient and cyclicity with respect to a set of initial vectors x. From the periodic behavior, we can classify MPL system into 3 categories. Boundedly periodic if the local transient exists for any initial vector and the global transient also exists. Unboundedly periodic if the local transient exists but the global one doesn't, and never periodic if the local transient doesn't exist for all initial vectors. We call an MPL system periodic if it is either unboundedly periodic or boundedly periodic. The following propositions relate the periodic behavior with lasso. First, an orbit is a lasso if only if the initial vector admits local transient and cyclicity. In fact, if an initial vector admits a local transient L and a local cyclicity C, then the corresponding orbit is a KL lasso where K equals to L plus C minus 1. Second, an MPL system is periodic if only if all orbits are lasso. We now move to the discussion to satisfiability model theory or SMT. Generally speaking, SMT refers to a problem to determine the satisfaction of a first-order logic with respect to a specific background theory, such as Boolean, bit vectors, real and integer arithmetics. For example, this formula has no solution over integers, but has solution for real numbers. One of the common logic used in SMT is linear real arithmetic or LRA, where the atoms are in the following form. Real difference logic or RDL is a sublogic of LRA where the atoms are restricted to this form. I will show that the syntax of max plus algebra can be expressed into RDL. First, the max plus operation can be expressed as an RDL formula. As a result, each MPL system can be expressed as an LDL formula as follows. We use this notation to denote the SMT variables to represent the states of MPL system at the K bound. Next, any max plus inequality can be expressed as RDL formula. Here we have F to represent a max plus inequality with the same set of variables. It can be reduced into F star by removing some variable with the corresponding scalar. Indeed, we can ignore any variable whose the scalar is equal to minus infinity. Then for each k where xk remains on both sides, we compare the scalar ak and bk. If this condition holds, we remove xk plus bk from the right hand side. Otherwise, we remove the xk plus ak from the left hand side. This ensures that the variables xk cannot appear on both sides. Finally, f star can be expressed as RDL formula either in conjunctive or disjunctive normal form. We now will discuss the model checking of MPL system via SMT. Considering the fact that the dynamics of MPL system represent the timestamps of discrete events, it is natural to define delay or time difference as the atomic propositions. In our paper, the time difference or TD proposition is defined as follows. For this TD proposition P, we call P initial if K and L equal to 0. From the TD proposition, we can define TD formula according to the following grammar. Again, a TD formula is initial if all appearing TD proposition in F are initial ones. The satisfaction relation of a TD formula is defined over orbit of MPL system according to the following recursive rules. In a TD proposition, the superscript here simply represents the step bound of the variables, while the subscripts are the indexes of variables. Any non-TD proposition defined for a metric A, where one of the superscript is not equal to 0, can be translated to initial one thanks to max plus algebraic manipulations. The idea is that any proposition can be expressed as max plus inequality as follows, which later can be translated into an RDL formula. This process is called get initial. We define the time difference specification for the MPL system as linear temporal logic formula in positive normal form defined over initial TD proposition according to this grammar. We call this logic as time difference linear temporal logic or TD-LTL. We can say that TD-LTL is the generalization of TD formula with temporal operators. It is also possible to express a TD-LTL formula that contains non-initial TD formula f. We just need to use get initial procedures. The satisfaction relation for TD-LTL is also defined over orbit of MPL system as follows. Let's have an example. Consider a TD-LTL formula as follows defined for the MPL system generated from this railway network. The specification phi assesses whether the railway network eventually reaches a state after which the delays of consecutive departure from both stations are always between 3 and 5 time units. All TD propositions in phi are non-initial. The transition into the initial ones are demonstrated as follows. Then we can verify the satisfaction of the specification for the following orbit. It is easy to check that the propositions are satisfied by the states of MPL system from bound 1 until 4. In fact, the propositions are satisfied for bound greater than 4. In general, if the orbit is periodic with transition L and cyclicity C, then we only need to check up to bound equal to L plus C minus 1. The verification problem for MPL system are defined as follows. Given an MPL system with a set of initial condition X and a TD-LTL formula phi, check whether all orbits starting from X satisfies phi. We assume that the underlying MPL system is periodic and X can be expressed as an LRA formula. Due to the first assumption, all orbits are guaranteed to be periodic and in Lazo shape. Also, the predict behavior determines the completeness threshold to verify the specification. From this consideration and conditions, the method's aim is to find the counterexample of phi or witness of its negation in the shape of Lazo. This notation denotes the witness of a TD-LTL formula over a KL Lazo at position M, where M is between 0 and K. Here we have the witness encoding for its operator, next, until, release, eventually, and always, the Boolean connective, conjunction and disjunction, and also for a TD proposition. Finally, this formula is satisfiable if only if there exists a KL Lazo pi such that pi doesn't hold the specification phi. Each disjunct here have different representation. The first one corresponds to the orbit of MPL system up to bound K, the second one represents the counterexample, and the last one represents the looping constraint. From this illustration of KL Lazo, the looping constraint is this formula. Here lambda is the eigenvalue of the state metric. It is straightforward to see that this whole formula is actually a non-initial TD formula. We can get the initialized version as follows. In this instance, we don't need to include the first conjunct since all propositions are initial ones. The drawback for the initialized version is that it may yield a lot of propositions. However, on the positive side, it only involves one set of variables. Now I will explain two types of procedure that we have developed. The first one is incremental procedure. For the inputs, we have an MPL system characterized by metric A, a set of initial condition X, a TD-LTL phi, and a positive integer n. On the other side, we set the value of transient and cyclicity into the smallest possible for both 0 and 1 respectively. Then we set L plus C minus 1 as the length of Lazo. From these values and together with the eigenvalue of the metric, we generate the formula that represents the orbit of MPL system up to bound K, the counterexample of phi over KL Lazo, and a looping constraint. By using an SMT solver, we check the satisfaction of the formula. If it is satisfiable, then we can conclude that phi is invalid. Otherwise, we need to increase the bound K. Instead of increasing it by 1, we use SMT solver to check whether there exists another orbit with transient greater than L and cyclicity that not divide C. This can be done by checking the satisfiability of this formula. If it is satisfiable, then we update the values of L and C as well as the bound K, and then repeat this process. In the case of SMT checking report unset, we can conclude that the current values of L and C are the largest possible, which implies that the specification is valid. It is possible that we may never exceed the procedure with these two outcomes. We use capital N as the other termination condition, which only tells us that there is no counterexample up to bound N. This output may occur on unboundedly periodic MPL systems. We call this procedure unrolled incremental. In comparison with the classical PMC algorithm, there are three main distinctions. First, we always use a fixed value of loopback for each iteration. Such loopback correspond to the transient L. Second, we may find a large increment. And lastly, the completeness threshold is not related to the specifications. Instead, it is related to the periodic behavior of MPL systems. The initial version, which we call initial incremental procedure, only differs on how we generate the looping constraint and counterexample. Also, we don't need to generate the formula representing the orbit of MPL system. The second method is called upfront procedure, where we only need to search the counterexample with respect to the completion threshold. In our recent paper, we provide the algorithm to compute the transient and cyclicity of MPL system via SMT solving. The procedures are then called unroll upfront and initialize upfront. As mentioned before, the completeness threshold is related to the periodic behavior of MPL system. This can be summarized into this result. Furthermore, for boundedly periodic MPL systems, the proposed procedures are proven to be complete and the verification problem is decidable. On the other hand, for unboundedly periodic MPL system, the proposed procedures are semi-complete and the verification problem is semi-decidable. Finally, I will present the experiment to compare the performance of SMT-based procedure versus the abstraction-based technique which can be found from these two papers. The IC3-based algorithm using NUXMV is also presented as a baseline. IC3 stands for Incremental Construction of Inductive Clauses for Indubitable Correctness. It is one of the most common algorithms used in model checkers. One of them is NUXMV, which is a symbolic model checker developed by Alessandro Cimati's group. There is a slightly differentiation on how NUXMV treats a lasso. It requires that for a KL lasso, the k plus 1 factor must be equal to XL. In the max plus setup, it can be achieved if the eigenvalue of the metric is 0. If the eigenvalue of A is lambda, then the eigenvalue of this metric is guaranteed to be 0. This motivates to modify the metric and then translate the dynamics of MPL system into the language that NUXMV can understand. After that, we pass it to NUXMV with command check LTL spec IC3. The setups for experiment are as follows. We generate 20 irreducible MPL system with dimension of n. There are n part 2 finite elements each row, where the values are between 1 and 20, and the locations are chosen randomly. For the specification, we generate 20 random TD-LTR formula, where the propositions are in this form. We generate the formula using spot, in which we set the number of operators and propositions into 10. The set of initial condition is the whole Rn, and we set 30 minutes as the timeout limit. The experiments are implemented for each pair of metrics and specification. These figures illustrate the performance of abstraction-based algorithm, IC3-based, and unrolled incremental. These three algorithms are similar in the sense that they unroll the dynamics of MPL systems. The scatter plots represent the running time for each pair of algorithm in logarithmic scale. Blue dots mean the specification is true, while red means otherwise. It is clear that the abstraction-based algorithm is the least efficient one. In fact, all experiments for 10-dimensional MPL system yield timeout. We then compare the performance of SMT-based incremental algorithms against IC3. It is evident that our proposed algorithms are faster. There are two reasons: the way we increment the step bound and a fixed loopback bound. It is also indicated by the plots that the initial incremental, which uses only one set of variables, is faster than the unrolled incremental, which uses multiple sets of variables. Finally, we compare the unrolled with upfront. It is expected that when the specimen is valid, the upfront algorithms are faster, since they only search the counterexample for a pre-completed completeness threshold. On the other hand, when the specimen is invalid, the incremental algorithms are faster, since the counterexample may be found at smaller bound than the completeness threshold. Interestingly, with an upfront algorithm, the one that employs one set of variables is again faster. To summary of this presentation, I will mention the main points. In our work, we have developed the novel SMT-based model checking of MPL system over time-different specifications. They are proven to be more efficient than the existing abstraction-based algorithm and also an alternative approach using NUXMV. This advancement mainly because of the SMT-based algorithm can be optimized via max plus algebraic transformation. We also proved that the SMT-based algorithm is complete, where the completeness threshold is related to the pair of transient and cyclicity. For the future work, we are interested to extend the procedure for non-periodic and non-deterministic MPL system. For these two models, the completeness of the procedure may not be applicable anymore.
Yeah, thank you very much. So Mohamed just wrote me in the chat that he might not be able to answer questions directly in Zoom, but he can answer in chat. But let's ask whether there are questions by the audience. Alex, you want to ask something? No. Well, given that we are indeed a little bit late, I think we can move to the next talk. But first, let's thank Mohamed. So, okay. So the next presentation or the next paper is by Florian Bruse and Martin Lange. It's about a decidable non-regular modular fixed point logic.
Hi, I'm Martin Lange and I'm presenting joint work with Florian Bruse on a decidable non-regular modal fixed point logic. So to start, I need to recall two things that are quite important. The modal mu calculus, here, this one, and the propositional dynamic logic over regular programs, which I assume that you are familiar with here. There are also other logics which might help you sort of put this in place, like CTL star, etc. They don't play a role here. So in this talk, we focus on these PDL-like logics where you write things down, for instance, like diamond A star P, saying there is a path along some A transitions to a state that satisfies P. Yeah, and the modal mu calculus where I express these things using fixed points, etc. So one of the characteristics of such logics here is that they are all decidable, that their satisfiability problem is decidable, and that's closely linked to the finite model property. But this is not all we know in this area of modal logics of programs. In fact, so there's also been a considerable amount of research going into undecidable logics. So for instance, into PDL over context-free languages. Clearly, if you can say things like diamond A star P, why shouldn't you be able to say things like diamond A to the N B to the N P? Meaning there is a path along which you see a word of the form A to the N, B to the N for some N ending in a state satisfying P. Okay, and there are also modal fixed point logics where we use fixed points, etc., to express such properties, especially this logic FLC here, which I will get to in detail in a moment. So, of course, the question now is, where exactly is the decidability border? How can we push this up further? And so far, this looks like, well, if you only use regular things, then you stay decidable. As soon as you use something as a non-regular in these logics, you become undecidable. And that's not quite true. So there's a logic called PDL over visibly pushed down languages, or called over recursive programs, where instead of arbitrary context-free languages, you are only allowed to use visibly pushed down languages. And this actually, so plugging this into this PDL mechanism gives you a decidable logic. And so this was the state of the art so far, before this paper here. So there are two maxima within the world of decidable program logics in terms of expressive power, namely the modal mu calculus, which can express all regular properties, and no non-regular ones, and this PDL over visibly pushed on languages which can express some regular properties but not all regular ones. Yeah, so therefore they're incomparable. And what we've done here is, so we've designed a new logic which sort of incorporates them both and remains decidable. Okay, so let's have a look at how this is done. So the first thing we need to do is need to look at what this FLC is. So if you look at the syntax, you will, and so first think, oh, this looks like the modal mu calculus. Yes, you have Boolean operators, fixed points, and then these modal operators. They're not, it's not quite the same. There are some subtle and important differences. So for instance, the modal operators in FLC, they're only they're constants, they're not unary operators. Then there is this additional sequential composition operator giving the logic the name chop, yeah, with chop, and then there is this additional sort of constant tau, which stands for termination. So that's just pure syntax, and I'll get to an example in a moment and see how this can be used. Just a small comment on the semantics of this logic. So it is actually possible to interpret this logic over transition systems, just like the modal mu calculus. And the idea here is that instead of reading a formula as a predicate, meaning something that defines a set of states, you read it as a predicate transformer, something that takes a set of states and returns another set of states. Yeah, that totally makes sense. Now, for instance, it totally makes sense to see that the diamond A operator is just a constant. Yeah, it's now takes a set of states, say T, and returns the set of states which have an A successor into T. So this is all semantically sound, yeah, and the important thing is that even that this fixed points can be interpreted in this standard way, in the sort of this function lattice with pointwise ordering. So let's not get into this anymore. So let's have a look at an example. The property I mentioned earlier, a to the n diamond, a to the n, b to the n, p. Yeah, so there is a path along which we see a word from a to the n, b to the n to some state p, can be described, can be expressed in FLC in the following way. So here's a formula, and let me just sort of go through this quickly so you see why this expresses this property. So first of all, I'll just use the variable x to abbreviate this entire fixed point formula here, and then what we can do is we can use fixed point unfolding, yeah, because it's a fixed point, it's equivalent to its unfolding. So basically say, okay, just this must be the same as tau or, and so on. And then we can use principles like disjunctions, they commute with sequential compositions, and tau actually denotes the identity predicate transformer, so this disappears. And then we can sort of unfold this fixed point again, and where we see, yeah, break up these disjunctions or the sequential compositions again. And so what we see, what actually happens is, so each unfolding, we sort of put out a new diamond A to the left and a new diamond B to the right. So this basically gives us sort of an infinite disjunction over formulas of the form diamond A to the n, diamond B to the n, P. Yeah, and then it's quite easy to see that that sort of from this infinitary modal logic, this formula expresses the same as this. Now, one of the crucial things here is that the crucial observations here is that in this logic FLC, there's no syntactic restriction on when to use a diamond and when to use a box operator. So I could just form the same and take this formula and just replace one diamond, this diamond B here, with a box B, and that of course is still an FLC formula, and the same considerations about how to unfold it, etc. hold. And what we'd see is that this actually then expresses something like, well, there is a path of the form a to the n for some n to some state, such that all paths of the form b to the n end in a state satisfying p. Yeah, and this is something you cannot do in these PDL-like logics, where you couple a context-free language with a single operator. Yes, it's all diamond or all box, yeah, but you can't combine them here in this way. Okay, so let's get back to the point here. We are interested in showing that this logic VP FLC, which I haven't defined yet, yeah, is decidable. So the first thing we need to do here is to characterize the satisfiability problem for this logic FLC syntactically. And I will not go into the details of this. This is a bit of a technical construction, and it really helps to know about game theoretic characterizations of satisfiability problem for the modal mu calculus. So the difference to that is that we don't work on sets of formulas, but we work on sets of stacks of formulas. Yeah? And so the stack is just sort of a sequential composition of formulas. The rest is very similar in that we have rules that operate on these formulas. In this case, actually just on the head of these stacks and the topmost formulas in these stacks. And again, so we have a game in where two players play against each other to determine satisfiability. The verifier chooses disjuncts in order to say, well, we can satisfy it this way, and the refuter chooses modalities to say, well, I don't believe that in this part of the model we can actually come to a conclusion here. Yeah, we can actually construct a model, yeah, and fixed points are unfolded, etc. And then there's what we need is some sort of machinery that tells us whether the unfolding of least fixed points is well founded. Yeah, and this is sort of a lot more complex, let's say a little bit more complicated than it is for the modal mu calculus. Essentially, we need to observe here that it's not enough to just look at occurring fixed points, but you also need to see what are the stack heights at these moments when a fixed point variable occurs. And I'll give you an example here to show you what this means. So here's an excerpt of a play in a satisfiability game on some formula, which is actually the conjunction of these two. Yeah? And I've sort of abbreviated a few things, like I've sort of applied two rules at the same time in order to be able to get a few of these configurations onto the slide here. So what's happening here, for instance, is we unfold a fixed point formula. This mu y, etc., this becomes y, and this nu z, etc., this becomes z, and then this y becomes the body of this fixed point formula, etc. Or here, for instance, we see that, yeah, so we have this stack on the left, separate comma from the stack on the right, and the stack on the left starts with a disjunction. So here we need to apply the rule for disjunction, which means verifier needs to choose some disjunct, and let's say she chose the right one here. And on this side, the head of the stack starts with a sequential composition, and then what's happening here is deterministically this is broken up, and so the two parts are being put onto the stack. This is how a stack may grow, and so on. Okay. Now observe that this stack here is actually already occurred up here, and they're actually connected, and this sort of is sort of the essence of this notion of a thread, yeah, which I have shown here partially, at least, with this sort of blue background color, yeah, which sort of shows where formulas were coming from. And the important thing here to see is that on this part, yeah, if we continued like this forever, which we could according to the rules, we would see this x and this y both infinitely often. But there's an essential difference, namely this y, so that's why it's not colored in blue, disappears at some point. Yeah, and we go back to a stack. Here we have a stack of height 3, and then we go back to a stack of height 2 only. Whereas the x just doesn't disappear. Yeah, it gets unfolded each time we go through this. And the y doesn't get unfolded, it just gets put there on top of the stack and it disappears again. And this is why this is, yeah, even though the outermost variable occurring infinitely often is of least fixed point type, this is still a good threat for for the verifier, because sort of the outermost variable that counts and occurs infinitely often is actually this x here. Yeah? And this is it's inner to this y. Anyway, so these are all the technicalities. So bearing these in mind, it is possible to show that these games are sound and complete with respect to satisfiability. The way to do this is to link them to model checking games. In fact, sort of a thread in the satisfiability game is essentially a play in the model checking game, yeah, with very similar winning conditions, etc. And this is how we can prove now. We can extract models from the game graph and so on. Now, this does not, so you may think that this may contradict FLC's undecidability. It does not, because the game graph is in general infinite. So there's no reason why these games should be solvable algorithmically. On the other hand, just because it's infinite doesn't mean that it cannot be solvable algorithmically. And in fact, I mean, there are classes of games played on infinite graphs which are solvable. For instance, stair parity games, which are solvable in exponential time. A stair parity game is essentially a parity game that's played on a visibly pushdown graph, and let's say a graph of a pushdown system, with a certain sort of extra condition. Not every position counts. Yeah, it's very similar to what I've just told you. So you need to look at the height of the stacks of a position. So let's say, yeah, it's like we get to some priority 7, and the stack height at this moment is, yeah, so we get to some priority 7, and the stack height at this moment here is 10, and afterwards it's only 9. So then this position is discarded. It's not a stair position. Yeah, so its priority does not count. So you only look at those stair positions, which are those for which the stack is frozen for the rest of the play. And then you evaluate the parity condition on this. Yeah? And it was shown that these games, they can be solved in exponential time. Now, this gives us a clear path to designing a syntactic fragment of FLC which is decidable. Yeah? Basically, all we have to ensure is that the formulas from this fragment are such that the satisfiability games that come out from these formulas are stair parity games. And the way to do this is to sort of look at the syntax of these logics, and what you will see is that the sort of the modal mu calculus kind of resembles right linear grammars by constructs like this, diamond a phi. As you do a diamond, you do something fixed here, and then you continue to the right. Whereas in FLC, you can do things like phi composed with psi, yeah, where you do something of arbitrary sort of length that can get you arbitrarily far through a transition system, and then afterwards you continue with something. It's a bit like context freeness. And how do we get to these stair parity games? Well, we need to find something that resembles visibly pushdown languages, are actually represented, for instance, by visibly pushdown grammars. Yeah, and this is what gets us to this logic visibly pushdown FLC. Yeah, where what we've done here is, well, we've employed the usual mechanisms of visibly pushdown languages, meaning, so first of all, what we need to do is we need to partition the symbols, yeah, the action symbols, into call, return, and internal symbols. And then the syntax is restricted in the following way. So you see, sequential composition can only be used in a very restricted way. For instance, if I use, if I use a modal operator with an internal symbol, then I can compose this to the right with an arbitrary formula from this fragment again, yeah, or just leave it out, so I just don't do anything to the right of it, or just continue with another formula. But if I use a call, yeah, if I use a modal formula with a call symbol, then I either have to follow it immediately by a return symbol, or I have to follow it eventually, so by a return symbol with something else in between, or so I follow it immediately by a return symbol, and then I continue afterwards with something else, or either of these, both. And the important thing is here, so these double brackets, they actually stand for either do a diamond or a box, doesn't matter. Yeah? And this is really what the essential difference to these PDL-like logics are, where you say commit to a diamond or a box, and inside of this you can now use a visibly pushed on language. And here what we do is say, well, use the mechanisms of visibly pushed on languages, of constructing them, but you don't care whether you use diamond or boxes at any sort of moment in there. Yeah. Okay, so why does this work? Well, the first thing to observe here is this lemma 1, which says if we take a formula from this fragment, then the plays in the satisfiability game on this formula, which are won by player verifier, they are recognizable by a deterministic stair parity visibly pushed down automaton. The way to do this is the usual trick of saying, well, we can design a non-deterministic visibly pushed on automaton that guesses sort of a mu threat. Yeah, and remember, this is exactly what the player verifier wants to avoid. Yeah, we can complement this, and actually we need it to be deterministic in a moment. And we can complement, determinize it to something that recognizes such a play when it's not got a mu threat, i.e. it's winning for player verifier. Yeah? And then the next observation is that the syntax of this formula guarantees synchronization between the stack heights in a configuration, namely that it can only differ at most by 1. Yeah, and whenever we play sort of the modal rules, and we do this eventually, then they are sort of synchronized again. Yeah? And this, then we can use the usual trick of saying, well, you know, a couple of stacks put next to each other, all of the same height, just looks like one stack. And this is why these satisfiability games played on this fragment VPFLC actually look like they're being played on a pushdown graph. And then we can put in this deterministic stair parity automaton from lemma 1 and turn this into a stair parity game. Okay, and this is, yeah, putting this together with a proposition 1 and this theorem 1, which said, so proposition 1 said stair parity games are solvable, and theorem 1 said that the games actually correctly characterize satisfiability problem, means that the satisfiability problem for this logic, this fragment VPFLC, is actually decidable in double exponential time. Yes, you get one exponent by the reduction to stair parity games here from this lemma 1, and another exponent by from proposition 1, which says stair parity games, solving stair parity games is exponential. Okay, so let me just conclude with 3 comments. The first comment is that there is a matching lower bound. It's very easily obtained. So this PDL over context-free languages can be translated into FLC. It's a linear translation. It's very straightforward. And if that gets specialized to this logic PDL over visibly pushed on languages, then you can look at the image of this translation. You see that actually falls into this fragment VPFLC. So given that a PDL over visibly pushed on languages is 2x time hard, we immediately inherit it from there. Yeah? The second thing is comment on the expressive power. So this fragment actually genuinely extends the world of decidable logics, in that we now have a logic that can express properties which are not expressible in either of those maxima within those decidable the world of decidable logics. Yeah, and so more on this is being presented this week at the Express workshop. And the last thing is, well, we do believe that the this VPFLC fragment can be extended a little bit further. You may have noticed that this termination formula tau is completely excluded from it, because having this causes some problems with the stack synchronizability and guaranteeing that the game is actually played on a pushdown graph. But there may be possibilities to include it and restrict it in a certain way so that we have synchronizability up to a certain bound, in which case we would regain decidability. Okay, that's it. Thank you very much for listening.
Yeah, thank you very much. So I saw that both authors are in the participants. So are there questions from the audience? I don't see a question, but then I have one. This, how was the name? The stair parity visibly push down automaton. Is there a chance to establish that they have exactly the same expressiveness as this? What was the name? Visibly VPFLC formulas.
Well, so first of all, it's a question of the models, right? So this automaton that we use there it works on linear sequences. So I mean, basically, so we use it to determine whether a play contains a new thread, right? And the play is just given as, you can see the configuration somehow as, actually the rule applications is the finite alphabet that the automaton reads, yeah? And then of course, so these logics are interpreted over transition systems. But of course, one could say, well, an infinite word is a transition system. Yeah. And then, then I think the expressive power is the same.
Yeah,
but,
okay.
Let's say 98% sure.
Okay. Mm-hmm. Are there other questions? No one is raising the hand or write something in the chat, so it seems to be not the case. Yeah, from Pedro, no question, but I like the talk. Well, me too. Thank you. Okay, so we can move to the next talk, which is about a temporal logic for strategic hyperproperties by Raven Beutner and Bernd Finkbeiner.
Hi everyone, and welcome to this talk about a temporal logic for strategic hyperproperties, which is joint work with Bernd Finkbeiner. So what's our work about? Well, on the one hand, we have hyperproperties. These are properties that refer to multiple traces in a system and are commonly used, for instance, in information flow control to specify properties such as non-interference. On the other hand, we have multi-agent systems. These are systems where we are usually interested in the strategic abilities of sets of agents. Now, ideally, we would like to reason about hyperproperties in multi-agent systems. But unfortunately, none of the existing hyperlogics allow us to express meaningful hyperproperties for such systems. And this is where our work comes in. What we do is we propose a new logic called hyper-ATL star that does just that. It allows us to express hyperproperties on the strategic behavior in multi-agent systems. Okay, so what's the outline of this talk? Well, I begin by introducing you to hyperproperties and an existing logic to specify such hyperproperties. I will then talk about multi-agent systems and the existing logic alternating time temporal logic. I will introduce our new logic hyper-ATL star. We will talk about model checking in both lower and upper bounds on this problem. And last but not least, we have evaluated a prototype model checker for a fragment of our logic. So let's begin with hyperproperties. And we can view them in contrast to trace properties. So trace properties are usually sets of traces that just specify admissible behavior of a program. Typical examples include something like a bad state is never reached or the program terminates. Hyperproperties, on the other hand, are sets of traces. So they allow us to specify relations between traces in our system, and they are commonly used, for instance, in information flow control. Properties such as observational determinism or non-interference are hyperproperties. And one of the most popular logics to express such hyperproperties is hyper-LTL. You can think of it as an extension of LTL, with explicit trace quantification. So formulas in this existing logic are built from the following grammar. So we have a prefix of universal or existential path quantifiers, followed by a formula that is almost an LTL formula, with the exception that we annotate these atomic propositions with the trace that they hold on. And in this logic, because we can explicitly quantify over traces, we can express hyperproperties. For instance, we could express observational determinism as the following property. Well, for all two traces pi1 and pi2, the output proposition on all of these traces should be identical at all times. And similarly, we can express a notion of non-interference where we ask for any two system traces, if their low input agrees at all times, so should their output. So this is a very powerful logic for expressing such hyperproperties. It is model checking, is fully decidable, and it has been studied extensively. As a more complex example in hyper-LTL, what we consider the following program. So what this program does is it continuously reads secrets from a high security source, and depending on whether this input is even or odd, it outputs either 3 or 5, where the star here denotes a non-deterministic choice between both of them. And in case it's odd, well, it outputs a 5 or 3. So in some sense, this program is clearly secure because by observing the output of this program, we cannot observe or not infer any properties about the input propositions. However, this program does not satisfy observational determinism because the non-determinism in our program can cause the program to output different values on different traces. So instead, what we want is a stronger property of non-interference called generalized non-interference. This formula now involves a quantifier alternation. What it says is, for all two traces pi1 and pi2, there exists a third trace that agrees on the high security inputs of the first and on the outputs of the second. So in some sense, this formula postulates that for every possible input sequence and for every possible output sequence, there exists a trace that agrees with both of them. So all inputs are compatible with all outputs. So this is a typical hyper-LTL formula. And in particular, because in hyper-LTL we resolve these quantifiers incrementally, this trace pi3 can be constructed knowing the entire traces pi1 and pi2. And as we will see, in some cases this is too strong. For instance, consider the following example. So on top here, I again gave this property of generalized non-interference. And the program we consider here consists of two subprograms, P1 and P2, and they are both almost identical. They both read a secret, and depending on whether this secret is even or odd, they either leak information or they don't. Now crucially, P1 assumes the input to be odd, otherwise leaks information, whereas P2 assumes the input to be even and otherwise leaks information. And on top of that, we have a scheduler that in each step can decide which of those two programs takes the next input. So if we now abstract this program by viewing the scheduling decision as the non-determinism in our system, this program satisfies generalized non-interference because, again, the trace pi3 is fixed knowing all the traces pi1 and pi2. But intuitively, what we want to specify in practice is not if there exists such a trace knowing the entire future input and output sequence, but we want to ask whether there is an actual scheduler or an actual strategy for this scheduler that only depends on the inputs and outputs seen so far. And in this case, this should clearly not be the case. So in some sense, the existing hyperlogic hyper-LTL, which is truly trace-based, does not allow us to reason about the strategy for the scheduler and only allows us to reason about the existence of a leakage disproving path, knowing all future inputs. So from the side of hyperproperties, we would like to reason about the strategic choices of agents with respect to our hyperproperty. Okay, so we can now look at multi-agent systems. So just as a very brief summary, multi-agent system essentially consists of multiple agents, and in each step, each of these agents submits a vote, and based on the combination of all of these votes, we select the successor state. So in particular, transition systems, which are like the typical model for temporal logics, can be viewed as game structures with just a single agent that in each step decides how to resolve the non-determinism in our transition system. Now, if you want to reason about such multi-agent systems, existing logic such as CTL star are not really appropriate. In CTL star, we could express something like there exists a trace that eventually reaches an error proposition. However, in a multi-agent system, we usually want to reason about the strategic behavior of a group of agents. So what has been done is there's been a new logic, alternating time tempo logic, which essentially extends CTL star by adding explicit strategies. So in this logic, we can express something like this, which asks, do the agents in the set A have a strategy to enforce that the error proposition is eventually true? So we do no longer talk about existentially or universally quantified traces, but about the strategic behavior of agents. The good news is this logic is still decidable. So it's 2x time complete to model check, which is much more expensive than CTL star, but still doable. The bad news is that this logic is not able to express hyperproperties, because in some sense, each path quantification ends as soon as we again quantify over a path. So on the side of multi-agent systems, we can already talk about strategies of group of agents, but we can't talk about them with respect to a hyperproperty. And this is exactly where our new logic hyper-ATL star comes in. So syntactically, our logic looks a lot like hyper-LTL. So what we have is, here I only gave a restricted fragment that corresponds to LTL. In fact, our logic is a branching term logic. But we have, in this restricted fragment, we have an initial prefix of strategy quantifiers, where the output of our game is bound to a path variable pi. And then we have again an LTL formula as for hyper-LTL. And the meaning of such a strategy quantifier essentially means, do the agents in A have a strategy such that when the result of this game is bound to pi, the remaining formula holds? So first of all, because before considering some examples, we can study how expressive is our logic. What we find is that it sits at a very nice place. So we have this hierarchy of temporal logics, where an arrow indicates one logic being a syntactic fragment of another. We see, well, on the left-hand side, we have hyperlogics such as hyper-LTL and hyper-CTL star. On the right-hand side, we have logics to reason about multi-agent systems such as ATL and ATL star. And our new logic, hyper-ATL star, subsumes both of these sides. So it's the first logic that can reason about hyperproperties and at the same time reason about the strategic behavior and subsumes all of these existing logics. So that's good news. Then the second question is this logic actually useful in practice? So let's look at some information flow control properties. And first of all, because we subsume hyper-LTL and hyper-CTL star, all of these existing properties that could already be expressed in these logics are already expressible in our logic. But in addition, we can express existing security properties that could not be expressed in these logics before. For instance, we can express simulation-based security, non-deducibility of strategies, or a strategic notion of non-interference. So just as an example of the strategic non-interference, here again is the formula of generalized non-interference, where the existential quantifier is in some cases just too strong. And what we can express in hyper-ATL star is this formula. So we no longer view our transition system as a transition system, but in fact as a game structure where we have a dedicated player to resolve the non-determinism of our system and a dedicated player that selects the input of our system. And we can now ask, for every trace pi1, does the non-determinism have a strategy to ensure that the output is identical? And because this is a strategy for the non-determinism player, he needs to resolve the non-determinism without knowing the future input selected by the high security input player. In particular, the example we saw before with the scheduler does not satisfy this property. And what we show in the paper is that, in fact, this is a stronger property. So if we have the strategic notion of non-interference, then there also exists a leakage disproving path. So we can express many interesting information flow control properties. And another area where we are very expressive are asynchronous hyperproperties. So why do we need this? Well, let's consider this simple program here. Essentially, we again read a secret input in each iteration. And then depending on whether this input is even or odd, we either flip our output proposition directly or we do so using a temporary variable. Now the problem is, intuitively the program seems secure because the output of the program is the same no matter what the input is. We just flip our output proposition, but most of the existing hyperlogics are synchronous in the sense that they traverse the traces of the system in a synchronous fashion. And if we consider this program, and for instance, we consider two traces, one where the red input is 0 and one where it's 1, we observe that the point of time where the output changes is offset. Namely, if the output, or with the secret that we read is 0, we flip to 1 step later. So synchronous formulations of, for instance, observational determinism do not hold on this system. But in fact, one could argue that because the attacker does not know the exact architecture that our program runs on, this program should still be secure. So we would like to allow this program to be stuttered and reason about an asynchronous version of, for instance, observational determinism. And what we can do in our logic is we follow the simple approach where we just add an artificial scheduling agent to our system that in each step decides whether the system progresses or whether it stutters. And if we then want to reason about the asynchronous behavior of our system, we can just talk about strategies for this scheduling agent. So if we again consider our example from before, on the left here we have these traces that do not satisfy the synchronous version. And if we introduce the stutter player, well, you can just stutter the state once and realign the output propositions. So the system from before with this added scheduling player, there does exist a strategy for the scheduling player to realign the propositions. So by viewing the scheduling decision as a strategic decision, we can also express meaningful and very intuitive asynchronous hyperproperties in our logic. And moreover, there do exist existing logics to express asynchronous hyperproperties, none of which have decidable model checking. And what we show is that for one of these asynchronous logics, namely asynchronous hyper-LTL, the largest known decidable fragment of this logic can already be expressed in our logic. So even though our logic is fully decidable, as you will see later, we can still express all the properties that are decidable in a logic that is in general undecidable. Okay, so after having introduced hyper-ATL and hopefully demonstrated that it is useful in various cases, ranging from information flow control to asynchronous hyperproperties, we can now talk about model checking. The good news first, like I hinted before, model checking of our logic is decidable. And what we show is that we can use alternating word automata to build an automata theoretic model checking procedure. In some sense, we use these automata to summarize all path assignments to outer quantifiers such that the formula is true. So what we do is, again, I will only give you a high-level overview over this procedure because the details are rather technical, but if we encounter such a strategic quantification here, we inductively obtain an automaton A phi of our subformula, we determinize this automaton, and we can then combine this automaton with our game structure by encoding the strategic behavior of the agents in the game structure within the transition system of our automaton. And by repeating this procedure, we in the end obtain an automaton over the singleton alphabet that is empty if and only if the formula does not hold. And if we look at this procedure, it seems like model checking is really expensive, because in some sense, determinizing an alternating automaton requires, in the worst case, a doubly exponential blowup. So how costly is our model checking procedure? Well, to answer that, what we can do is we can distinguish between two different kinds of quantifiers. On the one hand, we have simple quantifiers, namely existential or universal quantification if the agent set is empty or all of the agents are included, and we can have complex quantifiers, basically where neither of those two cases is the fall. So why is this important? Well, because if we have a complex quantifier, we really do need to determinize our alternating automaton, requiring a doubly exponential blowup, whereas in the simple case, a simple transformation from an alternating to a non-deterministic or universal automaton is sufficient. So what we get as an upper bound is that we can model check hyper-ATL formulas with k complex and L simple quantifiers in 2k plus L x time. And in fact, if we have at least one simple quantifier, we can do slightly better, namely in 2k plus L minus 1 x space. So model checking is decidable, but as for example for hyper-LTL, it is very expensive. What we show in our paper is that we can give a matching lower bound by encoding space-bounded Turing machines in the model checking problem of hyper-ATL star. So what we get is that model checking of such a formula with, again, k complex and L simple quantifiers is 2k plus L minus 1 x space hard, conditioned on the fact that we have at least one simple quantifier. So in total, we get this complexity table on the bottom here, where in some cases, for instance, if we have no strategic quantifier, we are essentially hyper LTL, whereas in the case where we have exactly one strategic quantifier, we are essentially ATL star and therefore 2x time complete. And in most of these cases, we are 2k plus L minus 1 x space complete. So we have upper and lower bounds on the model checking problem. Okay. Now the last thing, what we've done is we've evaluated and implemented a prototype model checking for our logic. And as our lower bound already suggests, model checking of the entire logic is just not possible in practice, because as soon as we have a lot of quantifiers and in particular many quantifier alternations, model checking becomes just too expensive to be viable on reasonably sized systems. So instead, what we focus on is a fragment of hyper ATL star that we call the self-composed fragment that can be checked efficiently. So this is a restricted fragment of this logic, but it is yet expressive. In particular, it subsumes all alternation-free hyper LTL formulas. All of these asynchronous formulas expressible in our system fall within this fragment, and we can even express existing approaches to hyper LTL model checking. And what we show is that hyper ATL star model checking of such restricted formulas can be reduced to the solving of a parity game. We've implemented our tool using Webanizer 4 to obtain a deterministic automaton, reduced this to a parity game that we then solve using PG solver. And you can find an evaluation in our paper, but essentially what we've done is we've constructed very small example programs and various security properties such as observational determinism, non-interference, simulation security, generalized non-interference, and so on and so forth, checked them on these properties. And on the other hand, we've also implemented many asynchronous hyperproperties, like asynchronous extensions of observational determinism or an asynchronous version of non-interference. Okay, so let's summarize. What we started off, we wanted to reason about hyperproperties in multi-agent systems. None of the existing hyperlogics could do that, so what we've introduced in this paper is this new logic, hyper LTL star, which can do just that. It can express meaningful and interesting hyperproperties on multi-agent systems. If we study the properties, we found that this is very expressive. In particular, it subsumes many of the existing hyperlogics and many of the existing logics to express properties in multi-agent systems. It can express various information flow control properties that could not be expressed before. Despite this expressivity, model checking is decidable for the full logic, which is in particular interesting because it can specify asynchronous hyperproperties for which none of the existing logics admit decidable model checking. And last but not least, there is a prototype model checker that can model check at least a fragment of our logic on concurrent game structures. So thank you for your attention. And if you're interested in hyperproperties and hyperproperties on multi-agent systems, I hope that you have a look at our paper.
Yeah, thank you very much. Yeah, are there questions? Martin?
Yeah, so thanks for the nice talk. I was a bit puzzled by the fact that both for the upper and the lower bound, the parameters that occur in there are the number of quantifiers. I would have expected something like the quantifier depth. I mean, intuitively, it should make a difference whether you say for all there is or for all something and there is something. So can you comment on this?
Yeah, so typically, for instance, what you do in hyper LTL, for instance, you don't count the number of quantifiers, but instead you count the number of quantifier alternations, because they only have universal and existential quantifiers. And essentially, if you have like a segment of existential or universal quantifiers grouped together, you don't encounter this exponential blow-up for each of them, because you can just group them together and essentially consider the composition of your structure. But in some sense, for the upper and lower bounds, you can just as well count the number of occurrences. So in our logic as well, if you have multiple existential quantifiers grouped together or universal quantifiers, you can group them together and consider the self-composition instead. But as soon as you have these more complex quantifiers that are no longer existential or universally quantified, even if you have the same agent set in multiple quantifiers, you still need to resolve them and need to determinize the automaton for each of them, because essentially we resolve these quantifiers incrementally. So we really do need to solve the inner games before we can talk about the strategies for the outer ones.
Okay, I'll have to think about this a bit more. But so, thanks. I have a second question, if I may, while I'm talking. So next thing is then alternating time new calculus, right? So in this case, hyper alternating time new calculus. Would that be the next thing to look at for model checking? Or?
I guess it could make sense. So I mean, right now, I'm not aware that there's a hyper extension of this. At least I'm not aware of any. But I guess you could, first of all, I mean, there is not much work going on, for instance, on the simple mu calculus, a hyper version of that, which would fall more into this traditional area, for instance, where hyper LTL and hyper CTL star sits. So I think if one were to study something like that, you would first, or it would make sense to study these logics first, and then try to get this alternation within your logic itself to again reason about strategic behavior, multi-agent systems, and so on and so forth.
Yeah, it's just all the techniques you mentioned there, they sound like, well, it wouldn't be surprising if they also worked for a alternating time mu calculus beyond ATL star. Yeah. Mm-hmm.
Yes, I think that makes sense. I mean, essentially, for instance, the model checking ideas, the technicalities differ, but the general idea, for instance, if you compare our model checking problem to the model checking problem for instance, hyper LTL or hyper CTL star, the idea of using these automata to summarize satisfying assignments, they are similar. So I guess you could extend that further, but future work, I guess.
Yeah, thank you.
Mm-hmm.
Thank you. Are there other questions? I see none. So then, thank you very much for the nice presentation. And this is indeed the end of this session. So I thank all the speakers, all the audience for coming and asking questions, in case you did. Yeah, so goodbye.